My project is about solving a linear system, AX equals to B. During the class, we talk about the method of steepest descent. We start at an arbitrary point and slide down to the bottom of paraboloid. We take a series of steps until we are satisfied that we are close enough to the solution. Steepest descent often finds itself taking steps in the same direction as earlier steps, so it would be better if every time we took a step, we got it right the first time. Here's an idea. Let's pick a set of orthogonal search directions, and in each direction, we will take exactly one step, and that step would be just the right length to line up. And as we can see from the picture, it took some steps to converge to the ideal error. The conjugate gradient method aims to solve a linear system AX equals to B where A is symmetric without calculation of the inverse of A, just like the steepest descent. But it only requires a very small amount of memory. Hence is particularly suitable for large-scale systems, and it begins with a guess at x, usually 0, and improves it step by step. The theory of conjugate gradient is quite pretty. For now, we will focus on what conjugate gradient does rather than why it works. Because unfortunately, optimization problems do not always have circular bow error surface, so we use conjugate directions instead of orthogonal ones, and then it is as if we were solving our problem on a circular bow surface. All that is needed now is a set of conjugate directions. Fortunately, we can find those using conjugate Gram-Schmidt process. We will need n conjugate directions. First, we take n linearly independent vectors. For example, residuals we use in the steepest descent will do nicely because we select each next residual to be orthogonal to the previous search directions, and right now I will only mention that Gram-Schmidt process is a method we will use, and later you will see how it works and what it does. And we can see from the picture that it reached the solution to the ideal error in only 2 steps. And here I use A as a 2x2 matrix. It's easy to find inverse for the for A. However, when A is a large linear system, the conjugate gradient method will have overwhelming advantage over the finding inverse matrix.